Hello everyone, welcome to our video lecture series on HYSYS and UNISIM simulations. Today we are going to discuss another case study using HYSYS and UNISIM. This will be mainly on a reactor, and it will be an extension of a problem we have already discussed in our previous video lectures. These lectures have been organized by www.Unitoperation.com, and my name is Shekhar Bhattacharjee. So let us first discuss the problem we have already solved in a previous video lecture, and then we'll show an extension of this problem. And the problem we have already discussed and shown the simulation in just the previous video lecture series is that toluene is produced from normal heptane by dehydrogenation over a chromium oxide catalyst. So this is my normal heptane, and this is my toluene, this is my hydrogen. So the toluene production process is started by, so let's show the PFD here. Here, as you can see, the toluene production process is started by heating 100 kilomole per hour. So that's my feed flow rate of normal heptane, at atmospheric pressure. So this is at atmospheric pressure in the feed from 20 degrees Celsius to 425 degrees Celsius. So in this heater, we heat 100 mole of normal heptane from 20 degrees Celsius to 425 degrees Celsius. That's a reactor temperature. So the reactor is maintained isothermally at 425 degrees Celsius, and it's an atmospheric pressure reactor. The reactor, the catalytic reactor, of which of course contains a chromium oxide catalyst, operates at 425 degrees Celsius. So it is also isothermally at 425 degrees Celsius, and of course 1 atmosphere pressure. And converts 15 mole percent. So the conversion purpose conversion is 15 mole percent of normal heptane to toluene. Its effluent, whatever the effluent comes out, so the effluent comes out, of course, is so this is my stream 3. So this is my stream 3. So this contains unconverted normal heptane and of course toluene and hydrogen. So this stream comes out, and then it is cooled in a cooler to 20 degrees Celsius. Of course, this is going to be a train of coolers, not just a single cooler, and then it is fed to a flash separator. So this is my flash separator. So this is my vapor stream coming out, and this would be my liquid stream coming out. So this is my vapor. Let me write it nicely. So this is vapor stream, and this is the liquid stream coming out, and we have to use Peng-Robinson equation of state. So we have already solved this, simulated this problem in our previous lecture series, and mainly what we can say that we have calculated what are the compositions and everything, but we just want to tell you the basic features of this simulation here. So here, as you can see, this is my feed. So this is my feed, and this is my preheater, and this is my preheater. So this is at 20 degrees Celsius, 1 atmosphere pressure. So here you can see this is the feed coming at 20 degrees Celsius, and here this is heated in this heater to 425 degrees Celsius. So this temperature is 425 degrees Celsius. So this now enters this reactor here. This R button, of course, you have to keep a liquid stream, although there will not be any liquid stream coming out at this particular temperature. So this is mainly a gaseous stream coming out. So this really contains normal heptane, unconverted normal heptane, and of course toluene and hydrogen. And this really comes out, as you can see, this is my feed, pure normal heptane. This is my R feed, which is right here, which is the same as normal heptane, and the R product of course contains the unconverted normal heptane and the product of toluene and hydrogen. So these are my mole fractions here. So this is of course at 425 degrees Celsius, and comes out, and then it is cooled in this cooler to S feed, and S feed temperatures, as you can see, 20 degrees Celsius. All along this is 1 atmosphere pressure. So this is, all pressures are 1 atmosphere, and this of course this is flashed into a vapor stream and liquid stream. So this is my flashed into vapor stream and the liquid stream, and the vapor stream of course contains mainly your normal heptane, unconverted normal heptane, and the hydrogen, and the liquid stream contains all these three compounds. And one thing I just want to show you, that's a heat duty on this one, heat duty on Q feed, that's a heater here. So this one right here is 1.35 10 to the power 7. So that's my kilojoule per hour of heat duty is required to heat the feed from 20 degrees Celsius to 20 degrees Celsius to 25 degrees Celsius. So that is the amount of heat duty required. So this is important because the statement of our next problem depends upon this particular value. So let me go what we are going to write right now. So in today's problem, what we're going to do is now we modify the process by preheating the feed stream to 315 degrees Celsius. So what we are going to do in the previous problem, we only had this preheater, but now what we are going to do, see here from the catalytic reactor, the product stream coming out, it goes into the heat exchanger. So this heat exchanger from the shell side, it enters the product stream and just comes out here, and in the tube stream, it, as it says, 100 kilomole per hour is heated from 20 degrees Celsius to 3. So we are actually recovering a large amount of heat from this product stream. So that is used to preheat the feed stream. So from now, in the next stage, in the preheater, we heat it from 315 degrees Celsius to 425 degrees Celsius. Of course, this heat requirement will be much smaller because we're using the heat content of this product stream to heat the feed stream to 350 degrees Celsius. Next, of course, it remains the same. So from the product which comes out, it just is cooled down here in this heat exchanger to preheat the feed, and then it goes to my cooler, and then of course the normal as it was before, it comes to 20 degrees Celsius, and this of course is my vapor stream, and this is of course my liquid stream. So the main modification is to install this heat exchanger to recover heat so that my heat duty of the preheater is reduced. So let us see how we do this problem in our HYSYS or in sim simulations. So let's go directly into this one. So we start a new case here, and of course we'll be using Peng-Robinson equation of state. So we go here, add Peng-Robinson equation of state here, and then we see the view components, then we add heptane, and then we of course add toluene, and then of course we add hydrogen. So these three components are added. So we just cross it out. So we have chosen the equation of state, which is Peng-Robinson equation of state, and we have chosen the components. So we just cross it out, and then we just define the reactions. We have described these things in details in our previous video lecture series. So what we're going to do, so global reaction set comes as a default. So we say add reaction, and this is a conversion reaction. So we say add reaction here. So what are the reactions here? So the components normal heptane, and the next component would be toluene, which is the products, and our next component would be hydrogen. And the stoichiometric coefficient, of course, for the normal heptane would be -1 because this is my reactant, and this product is 1, and this of course would be 4. We have shown these things in our previous lecture series. Let me quickly go here, and as you can see, we here, so this is my normal heptane, the stoichiometric coefficient is -1. This is toluene, the stoichiometric coefficient is +1, and this hydrogen stoichiometric coefficient is +4. Okay. So we come here, and the conversion is 15%. So overall, so we put here conversion as 15%. So once that is done, this is now ready. So the next thing that needs to be, so we cross it out, and the next thing that needs to be done is highlight this one, and it's a add to the fluid package, add set to the fluid package. So once that is done, now we can enter the simulation environment. Now in the simulation environment, it can be done in so many different ways. I'm just showing one of the ways. First, we add all the equipment here. So basically what we have, a heat exchanger, then we have a heater, then we have the reactor, then you have the cooler, and then we have the flash drum. So I'm just adding these in series as it is shown in this flow diagram. So we go here. The first thing is choose is the heat exchanger. The heat exchanger comes in, and then of course we have a heater. That's a preheater which we bring it in here, and then of course it goes to my reactor. For the reactor we have shown that these are my reactors, so we choose the, so these are my reactors here. So these are my reactors, and we choose the conversion reactant here. Then of course we have my cooler, so I bring down the cooler here, and then we have the separator, which is a flash drum. We cross it out. Okay, then slowly we define one by one. So this is my heat exchanger. In the heat exchanger, if you can see here, in the heat exchanger, let's say in the tube side, the feed comes in at 20 degrees Celsius, and so this is my stream 1, and the stream going out is stream 2. So we put here stream 1 coming in the tube side, and stream 2 going on the out of the tube side. Okay, and as you can see, then the shell side, actually this could be done the other way also. This product can go through the tubes and shell side, but that's a different considerations altogether. But anyway, in the shell side, the stream 4 comes in, which is the product stream, and it goes out at 5. So let's put this here in the shell side. This is going to be 4 and going out as 5. Okay, once that is done, then of course we have to put the parameters here. The parameters, we are assuming the pressure drop as 0 on the both on the tube side and shell side, which is not the case, but let's that's the way we do it. So we cross this one out. Okay, so now you see it's kind of like defined. So now we go to the heater. As you can see, the from the 2, the what is coming out from the heat exchanger goes to a preheater. So the stream is 2 is going to the preheater, and stream 3 is coming out of the preheater, which is going to the reactor. So we go here and we put stream 2 is coming to the preheater, and stream 3 would be going out of the preheater. And as we know, the pressure drop, we have to put this as equal to 0. So once that is done, and we have to of course add an energy stream here. So let's call the Q underscore preheater. Okay, so once that is done, we have defined this particular preheater here. So next what we're going to do, as you can see here, the stream 3, which is the preheated stream at 425 degrees Celsius, should be going to the reactor, and coming out of the reactor would be 4, which is going to the heat exchanger. So coming in is 3 and going out is 4. So we put here, we connect this one as 3, and going out would be, this is of course would be the vapor stream which would be going out. There will not be any liquid stream at that particular temperature, but we have to put it, so we just call it as a liquid. Of course there will not be, it will be zero flow, and the amount of energy that you have to take out is supplied, because this is a dehydrogenation reaction. You have to say Q reactor. Okay, so that is the heat load on the reactor. So once that is done, for the reactor, of course you have to attach a reaction which you have already defined. So we put the global reaction set, so that has been attached. So this kind of is defined. So as you can see, that as you can see here, that the stream 3 is coming in, and stream 3 is coming in from the preheater and is going to the reactor, and stream 4, the vapor which is coming in, is going to the heat exchanger. Okay, so next one is that the stream which is coming out, the product which is coming out of the heat exchanger, is now going to the cooler. So stream 5 will be coming out of the heat exchanger and it is going to the cooler, and from the cooler stream 6 will be going out. So let's put that way. So here we'll have this stream 5 would be coming to the cooler. So here you put here stream 5 here, and of course stream 6 would be going out of the cooler. And as you know that the pressure drop has to be put into 0, so we put the pressure drop equal to 0. So that and you have to define an energy stream. So the heat due to the cooler would be Q underscore cooler. Okay, so that pretty much defines the heat exchanger stream here. All right, so once that is done, now you can see from the heat exchanger, from the cooler, it comes, the stream 6 comes in and it enters the flash drum. So 7 is my vapor stream and 8 is my liquid stream coming out of the flash drum. So from the 6 would be input stream, 7 and 8 would be the output stream. So here we put as 6 as the input stream here, 6 as the input stream, and of course 7 would be the output stream here, and this 8 would be the output stream here. So that pretty much defines the entire flow diagram. So now the only thing that's now required is of course putting the defining the each stream. Okay, so this is an exact simulation, or this is a representation of my flow diagram here. What we have done here, we put in this flow diagram. Now we have to define the streams. Okay, so for the streams, as you can see, we go to the worksheet here, and for the streams, what we're going to do, we know first we define the composition here. We know this is pure normal heptane, so we just put normal heptane, pure normal heptane. So that's what the stream is defined. So let's go to the material stream. As you can see in the material stream, the feed is coming out at 20 degrees Celsius, 1 atmosphere, and 100 kilovolt per hour. So we go here and we put 20 degrees Celsius here, 20 degrees Celsius, and this is 1 atmosphere and 100 kilovolt per hour. So that pretty much defines what the feed stream is, as you can see. Okay, so what is coming out at 2? So in the stream 2, it would be coming out at 315 degrees Celsius. Everything is of course 1 atmosphere pressure, so this would be 315 degrees Celsius. So we put here for stream 2, the temperature would be 350 degrees Celsius. So that automatically defines what the stream 2 and of course the heat load on the system. So as you can see, these have turned deep blue, showing that these two streams are now defined. Okay, now as you can see here, stream 3 would be going at 425 degrees Celsius, and stream 4 would be also coming out at 425 degrees Celsius. So we go here, we put stream 3 at 425 degrees Celsius, and stream 4 will also be at 425 degrees Celsius. Okay, the moment you do that, you see all the streams here, everything is now defined all the way up to the cooler. Okay, so the only thing that remains is that we have to define the temperature of the cooler, which we know is it's cooled down to 20 degrees Celsius. So stream 6 temperature is 20 degrees Celsius. So we go here and we put the stream 6 temperature as, let's go down a little bit here, this is 20 degrees Celsius. So once we do that, automatically everything is defined. The entire simulation is now defined. So you can see, of course, the compositions will remain the same exactly as the previous one, because we have not changed anything about the reaction conditions. They remain the same. So the product composition will remain the same. But what is going to change is the heat duty of this preheater. Previously, we have to use a lot of heat to heat it from 20 degrees Celsius to 425 degrees Celsius. But now we have taken the heat from the reactor. So we have utilized the heat, that is enthalpy of the product stream, which is going in and it is coming out. So it is giving this heat to my feed stream. So it is utilized to heat feed stream to 315 degrees Celsius, which is now heated up to 425 degrees Celsius. So therefore, the heat load on this one will reduce significantly. Okay, so if you want to see that how much is my heat load, you can see here, and you see this heat load is now 3.287 times 10 to the power 6. So if we go here and we have just now compared what is the heat load. So I have given in the entire simulation and all the values here, and you can see if you compare with my previous one, that means this stream here, the very one where we did not have the heat exchanger. So we are comparing what was the heat duty here on this preheater, which heated from 20 degrees Celsius to 425 degrees Celsius, compared to slight modification here where we have used this heat exchanger to preheat the feed stream to 315. So what will be the heat load on this one right now? Same preheater. Of course, this will be much less, and that is because there will be an initial investment to buy this heat exchanger. But of course, on the recurring basis, regularly every day, you'd be saving a lot of energy, the cost of energy, because you'd be the heat load on this preheater would be much less. So let us see what are the values here. So the values here, as you can see here, without if for problem 1, this value was 1.36 times 10 to the power 7, and for problem 2, this is 3.29 times 10 to the power 6. So that's the difference. That's the amount of energy you'd be saving in per hour every day, just by installing this particular heat exchanger here. And of course, that really comes with an initial investment, but every hour you'll be saving money by saving on this energy requirement. So that's the way you do the simulation of a slightly more complicated flow diagram. I will see you in my next video lecture.